Seismic magnitude scales are used to describe the overall strength or size of an earthquake. These are distinguished from seismic intensity scales that categorize the intensity or severity of ground shaking caused by an earthquake at a given location. Magnitudes are usually determined from measurements of an earthquake's seismic waves as recorded on a seismogram. Magnitude scales vary on what aspect of the seismic waves are measured and how they are measured. Different magnitude scales are necessary because of differences in earthquakes, the information available, and the purposes for which the magnitudes are used. The Earth's crust is stressed by tectonic forces. When this stress becomes great enough to rupture the crust, or to overcome the friction that prevents one block of crust from slipping past another, energy is released, some of it in the form of various kinds of seismic waves that cause ground shaking or quaking. Magnitude is an estimate of the relative size or strength of an earthquake, and thus its potential for causing ground shaking. It is approximately related to the released seismic energy. Intensity refers to the strength or force of shaking at a given location, and can be related to the peak ground velocity. With an isoseismal map of the observed intensities in earthquakes, magnitude can be estimated from both the maximum intensity observed and from the extent of the area where the earthquake was felt. The intensity of local ground shaking depends on several factors besides the magnitude of the earthquake, one of the most important being soil conditions. For instance, thick layers of soft soil can amplify seismic waves, often at a considerable distance from the source, while sedimentary basins will often resonate, increasing the duration of shaking. This is why, in the 1989 Loma Prieta earthquake, the Marina district of San Francisco was one of the most damaged areas. Though it was nearly 100 kilometers from the epicenter, geological structures were also significant, such as where seismic waves passing under the south end of San Francisco Bay reflected off the base of the Earth's crust towards San Francisco and Oakland. A similar effect channeled seismic waves between the other major faults in the area. An earthquake radiates energy in the form of different kinds of seismic waves, whose characteristics reflect the nature of both the rupture and the Earth's crust the waves travel through. Determination of an earthquake's magnitude generally involves identifying specific kinds of these waves on a seismogram, and then measuring one or more characteristics of a wave, such as its timing, orientation, amplitude, frequency, or duration. Additional adjustments are made for distance, kind of crust, and the characteristics of the seismograph that recorded the seismogram. The various magnitude scales represent different ways of deriving magnitude from such information as is available. All magnitude scales retain the logarithmic scale as devised by Charles Richter, and are adjusted so the mid-range approximately correlates with the original Richter scale. Most magnitude scales are based on measurements of only part of an earthquake's seismic wave train, and therefore are incomplete. This results in systematic underestimation of magnitude in certain cases, a condition called saturation. Since 2005, the International Association of Seismology and Physics of the Earth's Interior has standardized the measurement procedures and equations for the principal magnitude scales: milliliter, EMS, MB, MB and MBLG. The first scale for measuring earthquake magnitudes, developed in 1935 by Charles F. Richter and popularly known as the Richter Scale, is actually the local magnitude scale, labeled milliliter or milliliter. Richter established two features now common to all magnitude scales. First, the scale is logarithmic, so that each unit represents a 10-fold increase in the amplitude of the seismic waves, as the energy of a wave is proportional to a 1.5. Where A denotes the amplitude. Each unit of magnitude represents a 101.5 approximately equals 32-fold increase in the seismic energy of an earthquake. Second, Richter arbitrarily defined the 0 point of the scale to be where an earthquake at a distance of 100 kilometers makes a maximum horizontal displacement of 0.001 millimeters on a seismogram recorded with a Wood-Anderson torsion seismograph. Subsequent magnitude scales are calibrated to be approximately in accord with the original Richter scale around magnitude 6. All local magnitudes are based on the maximum amplitude of the ground shaking. Without distinguishing the different seismic waves, they underestimate the strength. The original Richter scale, developed in the geological context of Southern California and Nevada, was later found to be inaccurate for earthquakes in the central and eastern parts of the continent. Because of differences in the continental crust, all these problems prompted the development of other scales. Most seismological